Hello, once again, all of you. Welcome. Today in the crash course, we start the D and S block element for grade 12. This is uh, inorganic chemistry part. So we don't have to do the P block here, but the D block and S block elements are very much there in our system. The chapter is quite easy. What we have to do is first we have to remember the first 3D series. So starting from 24 to 30 elements, we have to remember with their atomic. So let us start with this. Uh, D block elements. Let's see what are D block elements. D block elements are the elements which the valence electron D block elements are those elements where the valence electron, that is the last electron, comes in D or okay. Suppose we have 3D series, 4D series, 5D. We have to learn the 3D series in detail. Then we have to study 4D and 5D series. We have two important examples to relate. So let us start with the 3D series. Now, what is the 3D series? The elements which are coming from atomic number starting from 21 to 30. 21 is cambium, 30 is zinc. All the elements coming between vanadium and zinc are known as 3D series. Whereas 4D series, 4D, 3D, 4D is for us starts from 39, that is deuterium, to 48, that is CV that. And we have 5D series also. 5D series that starts from lanthanum and hafnium. Hafnium to mercury. Lanthanum to hafnium, hafnium HF to lanthanum to mercury. So these two elements are not here. That series. We can start with 58. It starts from between this between this two. That is uh, CSC 70. We have 6D series that called the actinium actinoid. Still is not that complete, it's an incomplete series. So we are still waiting for more elements coming in this series. Most of these are radioactive, radioactive, and you can say they are cheap and synthetic acids. Synthetic part is the general character. Characteristic of acid. So first of all, atomic rate. Suppose that has atomic rate. Now how does atomic radii, 3D or the 3D, 3D. So the atomic radii of transition elements are smaller than those of S dot and it is larger than that of P metal in the future. Okay. So these elements are smaller than S but quite smaller than. Now in transition series, the atomic number actually increases. So atomic radii first decreases till the middle of the series, become almost constant and then increases towards the end of the series. Right? The decrease in the atomic radii is beginning due to increase in the effective nuclear charge. So you see the graph given in the book that question is usually asked. Let's talk about the melting point of the first graph is melting point here. Okay. So this is the 3D series. Yeah, 3D series. What happens here in the 3D series? You can see that the melting point is increasing. Very cool. Then there is a drastic downfall in the melting point. Then again it increases, then it becomes almost constant, and then it becomes almost down in the case of copper. So why this happens? So melting point actually increases first because of the strengthening of the metal. Because of the strengthening of the metal. How does this metallic bond depend? So let us talk about vanadium. Vanadium is 21. The atomic number is argon. Still argon 18 electron substance. Then we have 5 carbon here and 4 electron. 21, 80, 90, 20, and 80. This is how we build the electronic circuit. After vanadium, let us talk about titanium. Here it is 2 argon configuration for this 4s2 and 80. Like this, when we are going down across the period, what happens here is the number of unpaired electrons in the atomic number 23 will be having configuration 4 and 2. Remember when you fill the electron, 4s orbitals are filled first. S orbital is more symmetrical and having more penetration potential and it has a more stability compared to p orbital. D orbitals are diffused in a large shape. So comparing D and S is more stable. lower atom. That is why we fill the electrons first in s orbital and then come to. So now if you go to 24 atom, then what happens? 24 is chromium and it has a exceptional configuration. It will have actually it means to have 4s2 in the 4 configuration, but because of the extra stability of unpaired completely half d orbital, one electron comes in. The configuration what we have is 4s1 3d 1. Now see, as we are moving 22, 23, 24, the number of unpaired electrons are increasing. So all these unpaired electrons are involved in making metallic bond. Metallic bond. So more the unpaired electron, stronger will be the metallic bond. Remember, more the unpaired electron, higher will be the metallic bond. Now, if you further increases the atomic number, then what happens? Now, with 25 Mn, you will see that the pairing of electrons starts again. So we have now pairing of electrons starting with 26 Fe. We will be having configuration 3d 7, sorry 3d6, 3d6, 4s2. So if we are going for 27, again the electron will get filled. So unpaired electrons are getting less. So what happens in the melting point? First, the metallic bonds increases, hence the melting point also increases because the unpaired electrons are increasing. Then it suddenly goes down. Okay, and if we reach to the last element of 3D series, that is zinc, what we find is it has completely filled orbitals, completely filled 4s and 3d10. So 4s2, 3d10, completely all the orbitals are filled and there is no unpaired electron, no unpaired electron. So unpaired electrons are not there, hence what we find, the metallic bonds in zinc is weaker. That is why we find the zinc metal is brittle. Why it is brittle? Okay, because the metallic bond of zinc are very weak. And why they are weak metallic bond? Because unpaired electrons in zinc's electronic configuration are not there. Okay, so metallic bond increases first, metallic bond becomes stronger and stronger, okay, as we increase the atomic number. But once the unpairing finish and pairing of electrons start, we find there is a decrease in the strength of the melting bond and hence the melting point also decrease. So this is the concept of the melting point. Enthalpy, okay, this is delta H, enthalpy of atomization. Okay, now atomization means how much energy. Suppose I have a iron solid metal here and I want to take out this atom out. I want to take out the iron atom out. So what is this energy called? Here I will call it enthalpy of atomization because I want these atoms in its gaseous state. I have to bring it in an atomic state, not in the elemental combined state. So I have to give energy. Now, definitely, if higher the metallic bond, if the metallic bonds are stronger, I have to give more enthalpy of atomization. The same, we have seen the same trend here. Now, see the metallic bonds increases here. So enthalpy of atomization increases. Okay, once the number of unpaired electron decreases, metallic bonds become weaker. Okay, and hence what we find, the atomization energy is also decreasing. So this is a trend which is again similar to that of metallic bonds or atomic and ionic size of the transition element. Because of this metallic bonds, you will find as the metallic bonds become stronger, okay, from starting and becomes strongest at the middle. What will happen? If metallic bonds are stronger, the atom will try to come close to each other. They will try to come each other. Okay, and the nucleus also pulls the uh, electron towards the center, and hence we find that there is a gradual decrease in the atomic radii, and then we find almost constant atomic radius. Okay, there is no gradual or a big increase. You can see from here till here, the atomic radius are almost similar. Okay, and this actually uh, is a reason why we can mix these metals to form the alloys, because of their similar atomic radii. Okay, so if you are getting, say for example, iron, okay, if we select or if we get the iron ore, there is full chances that we may get, along with iron, we get cobalt and nickel in the same mineral. Okay, so it's not only the iron ore, because these elements are having similar atomic radii. They can easily fit into the lattice structure of each other's compound, and we may get these metals together during metallurgy process. So here we have the electronic configurations, okay, for M plus, M plus 2 and M plus. Now let us talk about how do we get the metal ion. Say for example, iron. Let's talk about iron. Atomic number is 26. So we have 18 electrons till argon, and we have till 18 we have given the electrons, we still have uh, 8 electrons. Okay, sorry, uh, 18, 26, 60, 8 more electrons we have to fill. The first 2 electrons will go in 4s. The next 6 electrons will go here. Okay, so this is 3d6. 3d6. Now, if I have to remove 2 electrons from iron, that means I want to make it ferrous ion, 2 electrons. Now, which 2 electrons I have to remove? Remember, while filling the electrons, we have to fill electrons in s orbital first, and then leftover electrons in the d orbital. Now, while removing, also the same order we will follow. So, if I have to take out 2 electrons, I will not take it out from the d orbital, but I will take out from s orbital. So, Fe2 plus will be having electronic configuration argon with 18 and CD6 4s0. There is no electron in the 4s orbital. Okay. Now, if you compare this configuration of Fe plus 2 and Fe3 plus, Fe3, now Fe3 plus is argon. So one more electron from d orbital, I have to take it out. So there will be 5 unpaired electrons in d orbital. Altogether, I have taken 3 electrons, 2 electrons from s orbital and 1 electron from d orbital. Total 3 electrons I have taken out to become to bring iron into its spheric state. Okay, state, or you can say +3 state. This is parallel. Okay. +2 oxidation state, OD, set oxidation state, OS. Okay, so the out of these two, which is more stable? Definitely Fe plus 3 is more stable because it is having half filled orbitals of iron. Okay, so comparing Fe plus 2 and Fe plus 3, Fe plus 3 is more stable state. So iron, if you talk about +3 state, is more stable than +2 state for iron. Like this, you have to compare the electronic configuration of different elements in this entire chapter to see the stability. The basic rules which we have studied in grade 11, Aufbau's principle and the stability of the electronic configuration, completely filled and half filled orbitals are having extra stability. Okay, we have to discuss or give the priority to the stable state. Now, in first series, zinc is an exceptional case. What is zinc as an exceptional? Now, zinc with atomic number 30 is 3D element. 3D element. But we do not call zinc as transition element. Transition element. Zinc is not a transition element. Why? We don't call zinc as a transition element. So what is the criteria for an element to call to be as a transition element? Now, in transition element, a simple general rule, let's say argon, I'm not writing argon, let me write simple valence configuration, that is 3D10. 3D10, 4s2. So it has completely filled orbit. Now, it does not have any unpaired electron either in d or s orbit. Let us talk about the oxidation state of zinc plus 2. In zinc plus 2, which is another ionic state of zinc, we get 3D10, 3D10 and 4s0 configuration. Now, apart from these two electronic configuration, we have never seen any other configuration of zinc. So the existing possibilities of zinc either is zinc as an element or zinc as a +2 state, 0 oxidation state or +2 oxidation state. So in both of these states, we do not have any unpaired electron in 3D10. So for transition element, we must have at least one unpaired electron in 3D or 4D or 5D, or even say in d orbital. In d orbital, then we can call it as a transition. Now let us talk about copper. We can compare the copper with Cu is 29. I'm not writing the argon. Let us write the configuration. Actually, it should have a configuration 3D 9 4s 2. But what happens is 3D 10 and 4s 1. Now, if one electron comes from s to d orbital, configuration will become 3D 10 4s 1. Now, this second configuration is more stable, more stable. Okay. So what happens here is we find the exceptional configuration for copper as 3D10 4s 1. Now, copper, suppose if makes +1 cation, then what will happen? I will be having configuration 3D10, 3D10, and one electron from the s orbital will go as 4s0. So copper +1 or cuprous state is found here. Coming back to the zinc, why zinc does not form +3 state? Why we cannot take out electron from the 3D orbital? Now, if we have to take out an electron from 3D10, a lots of energy is required. Lots of energy is required. Okay, and if I give this much of energy, then the species, this resonant cluster will become highly reactive. So, which is not possible. Okay, a large amount of energy is required to disturb the 3D10 configuration. Now, coming to copper, but in copper, what do we see? We see copper +2 state is also available. Say, for example, copper sulfate. In copper sulfate, copper is +2 state and sulfate is 2-. Now, why the copper has lost his one electron? So it has a stable. See, this is how what happens in here. 3D9. Now, copper +1 has 3D10. The similar configuration what zinc +1 has. Sorry, zinc +2 has. +2 has. I cannot convert zinc +2 to zinc +3, giving reason that 3D10 configuration cannot be disturbed. But here, from copper +1, we can take out electron. Okay, so same 3D configuration we are disturbing. Now, why this happens? Now, this is only possible if copper +1 ions are in water. So, when copper +1 ion, or you can say copper +2 salt goes into the water. Okay, +2 copper ions get highly stabilized by hydrolysis. Okay, hydration, by hydration. What happens during the hydration? It gets surrounded by water molecule. By water molecule. All the water molecules, many water molecules surround it via oxygen being negative. So there is a hydration. We call it hydration. Okay. So this hydration is exothermic. Exothermic. And energy release here is so high that it compensates the ionization energy. Okay, so this high energy can be used to take out an electron from 3D10 configuration of the copper. So this is how copper +2 ion is formed. Okay, but in case of zinc, this is not possible. Zinc +2 ions, sorry, zinc +3 ion does not get uh, hydrated by water. Does not get hydrated. Okay, hence ionization energy, hydration enthalpy is not released, and we cannot get Zn +3. Fine. Ionization enthalpy, taking out an electron. So these are the common oxidation state. You will find that very commonly asked question in board exam is which transition element in 3D series has only one oxidation state? So this is vanadium. You will say that the zinc also has only one oxidation state. But the question was which transition element? Which transition element? Zinc is not a transition element, remember, because it does not have any unpaired electron. It's d orbital. So scandium is only transition element with only one oxidation state. Okay. If the question comes, which 3D element has only one oxidation state, then we have two ones. One is scandium, another is zinc. Zinc is not transition element, but it is a 3D element. But it comes in the 3D group, right? Which is having the highest oxidation state in, so that is 7. Okay, we have an element magnesium Og which shows +8 oxidation state. Okay, this is a newly discovered element as 118th element. If you don't remember it, it's fine, but for us, as per textbook, we should know that the highest oxidation state possible for any element is +7. Okay. So like that, there are some questions, give reason type questions, purely based on the electronic configuration. You must understand the electronic configuration of these elements to give answer to give reason type question. Now see for example here, why Cr plus 2 reducing and Mn plus 3 is oxidized, where both are having D4 configuration. Okay, so let us write this configuration first. Then the book you can solve it from there. But okay, solution is there. Cr plus 2 is reducing configuration D4 to D3. Let us write this configuration. Chromium.
Hello.
Yes, ma'am.
So please make me host. It has been lost from my hands.
Okay, sir.
Yeah, yeah.
Okay.
Done. Thank you.
This right here, chromium Cr. Configuration for chromium. Atomic number for chromium is 24. So it is D5 configuration. D5, D5, 4s1 configuration. This is again an exceptional configuration. We have already studied it. So the question says Cr plus 2. So let us make Cr plus 2 out of this. How to make Cr plus 2? We have to take out 2 electrons. So which 2 electrons we shall take out? So first electron will come out from s orbital, another will come from p orbital. Okay. Now another element is Mn plus 3. So let's stop Mn. So Mn is 25. Mn is number 25. So again I will be having 3d5 4s2 configuration. 5 electrons in d orbital and 3 electrons. Okay. So we are saying plus 3 oxidation states. You have to take 3 electrons. The first 3 electron I will take out from s orbital. I still have one more electron. So second electron, and now I have a third electron. Okay. Third electron is taken out. So guys, we have a similar configuration. Look at this configuration. Both of them are having similar configuration. 3D 4 4s 0. Okay. Remember the original configurations were 3D 5 4s2, and in this case 3D 5 minus 1. Here 3d5 4s2. Okay. Now Cr can easily shift itself to Cr3 plus. And for doing that, what we have to do? We have to take out this electron. This electron will come. Okay. And why this electron will come out? This electron will come easily. Okay, this one. But if you see this pair, d orbitals are further divided into two categories. That is P2G sets of d orbitals and EG set. Okay, and EG set. The d orbitals are further divided into 2Tg and EG. Now these are dxy, dyz, and dxz orbital, whereas EG sets are dx square minus y square and dz square. So if I take out one electron from EG, okay, then Cr plus 3 will form. And T2G set, see, T2G set is completely half filled. This is half filled. Okay, we don't have to see now d orbital as a whole. You can see that T2G is half filled by taking out 2 electrons. Okay, hence Cr plus 2 can go for plus 3 state PCB. Okay, that is more stable. Now for Mn, it can gain one electron here. Okay, and in gaining, what will happen? It will become Mn2 plus. Okay, so it can easily gain electron. That means it can show reduction, and if it further goes, can give electron. Okay, and it can further oxidize also to show us plus 7 configuration also, plus 5 configuration. Then say Mn plus 4. I can take out this electron. So if I take out one more electron, I will get stable T2G configuration. In that case, I will be having Mn4 plus configuration. So Mn has both the tendencies to go down to plus 2 and can go up to plus 4. Further also, it can show the oxidation state plus 7. So here Mn can be easily reduced and easily oxidized. Whereas in case of Cr, it is reducing only. Okay, it is a reducing. You can see this standard reduction potential values. If you compare the standard reduction potential values of titanium till rings, you will find the highest reduction potential value is of copper. Okay. And as we go up to the titanium, it is having the lowest reduction potential value. So these values can be helpful in comparing the reactivity of the metal. And you can see there is no continuous trend 1.63, 1.18, and again 1.18. See, look at the difference here. There is no gradual increase or decrease. So with the atomic size, as the atomic size is not gradually increasing or decreasing, there is no fixed trend of the metallic bonds or atomic size in the group. Fine. We do not find a gradual or one constant increase or decrease in the reduction potential value. So in the 3D series, The highest reduction potential value is for copper, and the least is that of titanium. So we have to so these are the questions with halides 3D elements forms. See chromium F6. F6 means here chromium is showing +6 oxidation. If zinc only 2 plus 2. Zinc does not have any further oxidation state. It has only +2 oxidation. So this is the data which you can compare. This paragraph again explains why certain valencies or the ions are more stable. How would you account for the increasing oxidation power in this? Okay. If you look at this, Mn has a +4 oxidation state here. Right? Those plus oxidation state here. Here chromium is having +6, vanadium is having +3 oxidation state. So how you will compare this? The stability here is due to the increasing stability of the lower species to which they are related. Okay. These in-text questions are important, and for this chapter, guys, mainly the question comes from the textbook. Mainly, the CBSE, the board exam does not do much experiment with this chapter. So direct questions have been seen from in-text or from the exercise part. Say, for example, these questions were the part of the board paper. These questions are also asked in the board exam. Magnetic property is because of the unpaired electron. More the number of unpaired electron, higher will be the magnetic property. If the compound or if the metal is not showing any magnetic property, we call it diamagnetic. That means no magnetic property. No magnetic property. Okay. Paramagnetic means it shows some sort of magnetic property. And magnetic property is because of the unpaired electrons. Okay. Why some are diamagnetic? Because of the paired electrons. And how to calculate the magnetic behavior? So magnetic moment is calculated with the formula n into n plus 2 Bohr magneton. Bohr magneton is a unit where n stands for number of unpaired electron. Paired electron. Okay. Any species which is having two unpaired electrons, so magnetic moment will be 2 into 2 plus 2 under root, which will give me 2 plus 2, 4 into 2, 8, and 2 root 2, 4 magneton. That is 1.41 into 2, and that's the answer for the fraction answer. This is the formula here. This is the magnetic moment calculated for different species. There is a text question. What will be the magnetic quantum, magnetic property, magnetic moment for the species D5? D5 means there are 5 unpaired electrons. So they have fifth and value is equal to 5. Formation of colored compounds. Why there is a formation of the colored compound? Remember, the d orbital has 5 suborbitals which are having T2G and EG set of orbitals. Now, T2G and EG are axial. The orientation of EG orbitals are on the axis, whereas T2G orbitals are having their orientation in the plane. So, depending on the position of the ligand, which we will be studying in the next coming chapter, the position of the ligand, okay, the splitting of d orbital takes place. That means all 5d orbitals which were having the same energy in the presence of some negative ligand, what happens? Their common energy, okay, is disturbed, and either T2G orbitals acquires a higher level, or in other cases EG orbitals acquire the higher uh, energy level. Now, in which case T2G actually takes a higher energy level? T2G, when we have a tetrahedral structure. Tetrahedral structure. We will study this tetrahedral complexes. Okay, and in which case EG takes the higher level when octahedral compounds are formed. Now, unpaired electron actually transits from D to D, from here to here. It keeps on jumping. We call it D to D transition of electron. Hence, this word transition element has been. So, when the sunlight falls on such complexes, electron jumps from lower level to higher level of d orbitals only. So, d to d transition. So, certain frequencies wavelengths are absorbed in this absorption of energy, and other frequency is reflected back. Okay, suppose 7 colors of the sunlight is falling on this complex, and the blue color is not absorbed. What all other frequencies are absorbed during this transition? What will happen? The blue color is reflected back. We see the blue color of this compound. What happened to the other frequencies? Other frequencies are used up by these electrons in jumping from Eg to T2G, or we simply call it D to D transition. Okay, so in that case, we find that the substance looks similarly. Different compounds, complexes absorb different types of uh, frequencies, and according to that, they imparts color in their compounds. Fine. Formation of the complex compound, guys, it is very much detailed even in the next coming chapter. There we can study catalytic properties, the d orbitals, d 3d series and d orbitals. D block elements actually behaves as a catalyst because of their comparatively large surface area and available empty d orbitals for the incoming particles. So they provide large surface area, variable oxidation states are possible, okay, and they provide the empty orbitals for breaking the bonds. Alloy formation, because they have almost similar size, we have discussed, so they can be mixed up together, okay, and the desired uh, properties of any solid can be obtained by mixing these elements. So alloys are possible. Okay. Oxides and oxoions. For this, we have to remember the preparation of K2CrO4, very, very important. Preparation of KMNO4 is very, very important. KMNO4 and K2CrO4. Preparation and few examples of this is very, very important. The structures you have to remember here, tetrahedral, okay, the tetrahedral permanganate purple color, and this is a tetrahedral green ion. Okay, so look at this difference. The structure here 2O minus 2 is there, here only minus 1. These examples, equations you have to remember. So with this, guys, D block element is finished. F orbitals, lanthanoid and actinoids, we will study in the next coming class. Okay. Fine. Anybody has a doubt? Fine. No doubts so far. So we are winding up this class, and we'll meet in the next class with the F block elements and their properties. Okay, and a quick recap of the entire chapter will take with doubt solving session. Thank you very much.